Welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communication systems. Alright, so today let us start looking at LMMSE estimation for multi-antenna channel estimation. Alright, so as we have seen in the previous module, the multi-antenna channel estimation problem corresponds to a scenario of a vector parameter estimation. Alright, so now let us look at how we can apply our LMMSE principle, that is the linear minimum mean squared error estimation principle, to the estimation of a vector parameter in the context of multi-antenna channel estimation. Okay, so LMMSE. So let us look at LMMSE, where LMMSE, as you know, stands for linear minimum mean squared error estimation. For multi-antenna channel estimation. In fact, multi-antenna channel estimation in a wireless system, correct? So we are going to look at LMMSE estimation for a multi-antenna wireless channel, alright, and we have already seen that the problem. So consider the multi-antenna channel estimation. So we have seen the problem can be expressed as y bar equals x h bar plus v bar, correct, where this y bar, this is your n cross 1 observation vector, x is your n cross m pilot matrix, and h bar is now your m cross 1 parameter vector. Previously we had a scalar parameter, now you have an m cross 1 parameter vector, and v bar is the additive noise, that is, this is the n cross 1 additive. This is the same as before, this is the n cross 1 additive noise vector, this is an additive noise vector, correct. And now if you look at it, what is n? Let us define this, let us recall these quantities also. N equals number of pilot vectors. N is basically the number of pilot vectors transmitted in the downlink by the base station. Remember, we are considering a downlink channel estimation scenario where n is the number of pilot vectors, m is the number of transmit antennas. There are multiple antennas, m is the number of transmit antennas. Recall that we are considering a system with m transmit antennas, a single receive antenna, correct, and n transmitted pilot vectors, alright, and therefore the pilot matrix x is n cross m, the observation vector y bar is n cross 1, this parameter vector h bar is m cross 1, right, and v bar, the noise vector, is n cross 1 as usual, as seen previously, alright. And now we are going to demonstrate or illustrate how to estimate this channel vector h bar, alright, and this is a vector parameter, okay. So now consider a Bayesian scenario. Remember, this is a we are talking about Bayesian estimation. Consider a Bayesian scenario. Bayesian scenario implies there is prior information about the parameter. Bayesian estimation scenario. Bayesian estimation scenario implies there is a parameter vector h, there is a prior information about the parameter, and in this case, since we are a parameter vector, h bar equals, what is this? We have a parameter vector h1, h2 up to hm, where these are the m channel coefficients, correct. These are the m channel coefficients, feeding channel coefficients rather. These are the m channel coefficients, and therefore h bar is a collection of m parameters. So, your h bar, this is your parameter vector. Okay. These are some things to remember. This is a parameter vector. We are considering the estimation of a vector parameter, and hi is the channel coefficient corresponding to the ith antenna. Hi is the channel coefficient of the ith antenna. All right. Now, previously, remember, whenever we consider previously, so far when we looked at Bayesian estimation, we have looked at MMSE estimation, correct, and we have considered the parameter h to be Gaussian in nature. However, in the previous modules we have introduced the LMMSE estimate, and for the LMMSE is valid for an arbitrarily distributed observation and parameter. Therefore, we no longer need to consider the parameter or the parameter vector to be Gaussian in nature, as long as we are willing to simply accept that it is only the LMMSE estimator and it is the best amongst the class of linear estimators. And since we are going to be using the LMMSE estimate, we are now not going to assume that, we are going to assume the parameter vector h bar can have any arbitrary distribution, not necessarily Gaussian distributed, and therefore we can simply use the LMMSE estimate without any problem. Okay. So, we are not going to assume any prior distribution for h, we are simply going to say that h is any arbitrary distribution with each coefficient hi having 0 mean, average power, average gain or expected value of magnitude hi square equals sigma h square, and further we are also going to say that this expected value of hi into hj conjugate, that is channel coefficients of two different antennas, this is equal to 0 if I not equal to j, implies hi and hj are uncorrelated random variables. These are, since the covariance is 0, these are uncorrelated random variables, and we can only, since the expected value of hi hj conjugate is 0, we can only say that these are uncorrelated, because we are not assuming hi hj to be Gaussian, we cannot say that these are independent. All we can say at this point, since we have not made any assumption about the prior distribution of h, right, we can only assume they are uncorrelated, and that is sufficient for the purpose of LMMSE estimation. We do not need to really assume that they are independent. As long as they are uncorrelated, we are only concerned with the uncorrelated nature. We are not really bothered about whether they are independent or not, because the LMMSE estimate simply considers the covariances, the covariance information. It does not need information about the probability density functions of h, the parameter vector h, and in fact also the observation vector y bar. Okay. So, that is something to keep in mind. Okay. And therefore, we have, since each element hi is 0 mean, if we look at expected h bar, naturally since each component is 0 mean, expected value of this parameter vector h bar is going to be 0. Further, if we look at this the covariance matrix, okay, to consider a simple scenario, I am simply considering a real scenario. Let us simply consider a real scenario. I am going to remove this complex conjugate. Just to make this estimation paradigm simple, consider all quantities to be real. Consider all these quantities to be real to begin with. consider all these quantities to be real. We are going to illustrate later how you can extend this to a complex scenario. Then what is going to happen, this expected value of h bar transpose, if you expand this, what is expected value of h bar? This is expected value of, well, take the column vector h1, h2, hl times h bar transpose, which is the row vector h1, h2 up to hl. Now, you can see when you multiply this column vector by the row vector, what you are going to have is all the diagonal elements are going to be elements of the form h1 square, h2 square, so on. The off diagonal elements are going to be of the form h1, h2, h2, h1. So, those expectations are going to be 0, because we are considering the different the channel coefficients corresponding to the different antennas to be uncorrelated, correct. So, just to write this more explicitly, I think probably if writing one more step will help, expected value of h1 square, the diagonal element, second diagonal element will be h2 square. So, on the last diagonal element will be, of course, this is m, this is m, this is hm square, and these entries are going to be of the form h1, h2, h2, h1 and so on. And if you look at the expected values of these, the expected value of these off diagonal elements are going to be 0, the expected value of the diagonal elements, expected value of h1 square equals expected value of h2 square, so on. So, these diagonal elements are going to be equal to sigma h square, all the off diagonal elements are going to be 0. So, this is going to be sigma h square times the identity matrix, and this is the, just to be clear, this is an m dimensional identity matrix. When I write I m, this means an m cross m identity matrix, because identity matrix is a square matrix, that is well known. So, I am going to simply write the number of rows or number of columns, they are both equal. So, this is I m basically denotes the m cross m identity matrix. So, we can say that expected value of h bar transpose equals sigma h square times the identity matrix, and this is also, you can call this as, in this case, RHH. Okay. Since we have parameter vector, you have a matrix, you have the covariance matrix RHH. Okay, expected value of h bar transpose, considering uncorrelated channel coefficients, each with gain sigma h square, each with average power sigma h square at each antenna. That means basically the covariance matrix expected value of h bar transpose, that is RHH, is sigma square times sigma h square times identity. Now, another assumption that we are going to make, which is also a valid assumption, is that the channel coefficients and the noise samples are uncorrelated, and this is a valid assumption because the channel coefficients are related to the channel coefficients of the radio propagation of the wireless environment, and the noise samples are the noise samples which arise because of the thermal noise at the receiver, correct. These two phenomena are basically independent. One, the channel coefficients are arising because of the scattering nature of the wireless environment, because of the reflections and the propagation in the wireless environment, and the noise is basically arising, the Gaussian noise at the receiver is arising basically because of the thermal noise property, the thermal noise in the circuits at the receiver, and these two phenomena are independent. So, we are going to assume that the channel coefficients and the noise samples are independent. In fact, as we already said, they are independent, but for our purpose we do not need independence, as long as they are uncorrelated, that is sufficient, alright. So, although they are independent, we are going to simply use the fact that they are uncorrelated, okay, which means that if you take any noise, if you take any channel coefficient expected value of Hi times any noise sample Vj, expected value of Hi times Vj, this is equal to 0 for all I comma j. Remember, we have m channel coefficient. So, 1 less than equal to I less than all. So, I can be any value between 1 and m, and we have n noise samples. So, j can be any value between 1 and n, and therefore, this basically arises because the noise comma channel are independent. Of course, independence means uncorrelated. For any random variables, if they are independent, then naturally they are uncorrelated. Okay. So, this is something to keep in mind, which means now, since any channel coefficient is uncorrelated with any noise samples, if I look at expected value of h bar times V bar transpose, this is equal to 0. In fact, this will be m cross n expected value of V bar times h bar transpose. Remember, V bar is n cross 1, h bar is 1, h bar transpose is 1 cross m. So, this will be 0 n cross m, correct, because the channel vector and the noise samples are uncorrelated. Therefore, expected value of h bar V bar transpose, expected value of V bar h bar transpose, both are 0. Okay. Now, let us look at the covariance of the noise, and this is something that we have already looked at, that is the covariance, that is we are going to consider the noise samples for the similar to previous scenarios. Similar to previous scenarios, consider V bar equals Gaussian noise vector V bar equals a Gaussian noise vector with covariance expected value of V bar transpose equals sigma square times identity. This implies basically that expected value of each, we are going to assume 0 mean noise. So, expected value of each Vi is 0, the noise variance, each noise is of variance, expected value of Vi square equals sigma square. Further, we are going to assume that the noise samples at two different antennas are uncorrelated. Since the noise is Gaussian, this implies also independence. If I is not equal to j, correct, noise samples at two different antennas are uncorrelated, correct. Noise samples at the different antennas, these are uncorrelated, correct. So, this is we have now described the statistics of the problem, correct. We have described the covariance matrix of the channel vector, covariance matrix of the noise vector, cross covariance of the channel and the noise. Okay. Now, let us find the LMMSE estimate of h bar. Now, we have all the ingredients to find the LMMSE estimate of the channel vector h bar. Okay. So, let us now proceed to find the LMMSE estimate and we know we have derived this expression. First, observe now that we have noise is 0 mean, expected of V bar equal to 0. We have channel is 0 mean, expected h bar equal to 0. This implies expected y bar equals expected x h bar plus V bar equals x times expected H bar plus expected V bar. Now, expected H bar is 0, expected V bar is 0. So, this is basically 0. So, we have expected value of Y bar equal to 0. So, basically we have expected value of Y bar equal to 0, expected value of H bar is equal to 0. So, the parameter expect is 0, 0 mean, observation vector is 0 mean. So, we can use the expression for the LMMSE estimate that we have derived previously. Okay. So, we have H hat will be R H y into R y y inverse into Y bar. This is the LMMSE expression for the LMMSE. This is the expression for the LMMSE estimate. So, now we have to find these two quantities. We have to find R H y and R y y and R y y inverse. We have to find these two quantities. So, now let us start with R y y. R y y equals expected value of y bar transpose, which is equal to expected value of, this is equal to expected value of x H bar plus V bar into x H bar plus V bar transpose. Using the properties of the transpose, this is basically x H bar plus V bar times H bar transpose times x transpose plus V bar transpose. This is equal to expected value of x. Now, let us take the product term by term, x H bar transpose x transpose plus V bar H bar transpose x transpose plus x H bar, I am taking the product by term taking the product V bar transpose. And now, if you take the expectation operator inside, you will get x expectation of H bar transpose x transpose plus expected value of V bar H bar transpose x transpose plus x expected value of H bar V bar transpose plus expected V bar transpose. Now, we have already said that the noise and the channel are uncorrelated. So, therefore, expected value of V bar H bar transpose, expected value of H bar V bar transpose, these are both 0. Expected value of H bar transpose, this is sigma H square times identity. We have already derived that. Expected value of V bar transpose, this is sigma square times identity. This also we have derived. So, this becomes sigma H square. So, let me write this, x times sigma H square times identity matrix into x transpose plus sigma square times identity, which is basically sigma H square is a scalar. So, bring it out, this becomes x transpose plus sigma square times the identity matrix. This is your this is your covariance matrix R, this is the covariance matrix R y y, this is the covariance matrix R y y. Okay, R y y, the covariance matrix, which is the expected value of y bar transpose is sigma H square x transpose plus sigma square times identity, where x, of course, you can remember, you can recall this is the pilot matrix. Okay, and observe that this is the dimension of this matrix. Observe that this is n cross m, this is n cross m. So, R y y, this is n cross m, m cross n. So, R y y is basically n cross n. this identity matrix is naturally also n cross n. Now let us look at RHY, R the cross covariance matrix of H comma Y. RHY is expected value of H Y bar H bar Y bar transpose, correct. This is equal to expected value of H bar times X H bar plus V bar transpose, which is equal to expected value of H bar transpose X transpose plus V bar transpose equals expected value of H bar transpose X transpose plus H bar V bar transpose. Expanded it term by term, again take the expectation operator inside. This is going to be expected value of H bar transpose X transpose plus expected value of H bar V bar transpose. Noise and channel are uncorrelated, expected value of H bar V bar transpose is 0. This is equal to expected value of H bar transpose. We have already seen this is sigma H square times identity. So therefore this becomes sigma H square times X transpose. This is your R H y, this is your R H y. So we have now both the quantities, we have R H y, we have R y y. Therefore the channel estimate is H hat is equal to R H y into R y y inverse into y bar, that is the LMMSE estimate. Now we are going to substitute these quantities to derive the LMMSE estimate. So therefore now the LMMSE estimate is given as LMMSE estimate of H bar is H hat, this is H hat equal to R H y, which is sigma H square times X transpose R y y inverse sigma H square X transpose plus sigma square times identity, this is n cross n identity matrix inverse into y bar. This is your expression for the LMMSE estimate. This is the expression for the LMMSE estimate of the channel vector H bar. Let us write this down again. LMMSE estimate of channel vector H bar for multi antenna downlink wireless So multi antenna downlink wireless channel estimation, that is H hat equals sigma H square X transpose times sigma H square X transpose plus sigma square identity inverse times the vector y bar, where y bar is the observation vector. Okay. So we have derived the expression for the LMMSE estimate of the channel vector, and therefore we have illustrated basically the general principle of LMMSE, that is linear minimum mean squared error estimation of a channel vector. Previously we have only considered scalar parameters, now we have extended to a scenario with vector parameter. Okay. And further there is a way to simplify this expression for the estimate further, which we are going to do in the subsequent module. So this module basically involved applying the principle of LMMSE estimation to the estimate, to derive the channel estimate, derive the estimate of the channel vector of a multi antenna wireless communication downlink scenario. Alright, so we will stop here. We will simplify this estimate expression for the estimate further in the next module, and we will also derive the mean squared error, that is a mean squared error or the mean squared error of this LMMSE estimate. So we will stop here. Thank you very much.